Okay, so this is the second question from homework 4, which was a big disaster. I will explain. Let me solve you out how it does. First, I forgot to mention this definition, but I assumed that it was kind of obvious, like you could infer what was epsilon because I stated assumption 8 without defining epsilon. So I like that was a mistake, but pretty natural definition, I think. And then, first let's think about omega to calculate the optimal weight. Omega takes this form, so using the homoscedasticity assumption in assumption 8, sigma squared. So this much was epsilon. So it's GG prime will look like this using the homoscedasticity. So 1z squared. And inverse, obviously, goes like this. And we have very familiar form, a variance of z here. Okay? But anyhow, it does not matter. Uh, and again, when you implement the optimal weight matrix, you do not need to calculate sigma squared, which is the variance of epsilon. You do not need to calculate the variance of z because these positive constants do not affect your minimization problem, right? So I will ignore them and I will only take this part, the matrix part, right? So just calculate all the things this way, this. Then you don't need a two-step. You don't need a preliminary parameters to calculate the weight. It's already optimal weight without calculating those constants. Okay, so that's what I suggest. And here, this was the problem. For consistency, we have to verify these 5 assumptions. And actually, you can find them on the like in the proof. And 1, 2, 4, 5, 1, 2, 3, 5 are obvious. So nothing much to discuss. So, but number 4 was the problem, right? Dominating function. We need to find the dominating function that has finite expectation. So, like I will show you the proof, but I thought it was not that difficult, right? But actually it was. First, I should have assumed G is positive. And it is natural because in our setup, G is the consumption divided by previous consumption. So if we assume consumption is always positive, then obviously G will be positive, right? So I should have had this assumption because if it was negative, G to the exponent of minus gamma could be a complex number, right? So something like 1 over root minus 1, right? That's anyhow, it is not, it's technically required, but does not change the argument that much. Now, the second problem is this. So to bound, like basically main problem is this part, right? G2 minus gamma was the main problem. That part, we need to bound that. But to do that, we have to divide 2 cases. Like if G was greater than 1, then for any positive gamma, G2 minus gamma is smaller than 1. So we don't need to bound. And of course, obviously it is positive, but it is smaller than 1, so it is so simple if this was true. But if the consumption is smaller than 1, then the story is a little bit annoying, right? So if it's negative smaller than 1, then we have to bound the G2 minus gamma using the upper bound of gamma because it is increasing in gamma, right? That means we have 2 different cases. We have to think about G greater than 1, G smaller than 1, and then in that case, we are going to bound the we are going to bound using this random variable mt. So it is combined maximum in both cases. We take the maximum of those two cases, right? So it will be upper bound either g greater than 1 or smaller than 1. But so what I regret is I should have assumed it, right? If I gave you the assumption that g is greater than 1, then the bound is upper bound is just simply 1. So then the problem was much easier, right? That's what I should have done. But because I didn't do that, I have to think about this problem. Oh, then our total bound of the bigger term, beta rt2 minus gamma minus 1 can be bounded by, like, first, absolute value of something minus something can be written as absolute value plus absolute value of the other, right? So I put minus 1 outside of the absolute value. And multiplication can split the absolute values, right? Like this. And beta is bounded by beta u, upper bound. And r is bounded by b. And g2 minus gamma was bounded by m here, right? But like as I said, if we assume this, which means consumption is ever growing, then this bound would be simpler, 1. Anyhow, this is what I found. And then come to take care of the instrument, I will just use 1 is bounded by 1, z is bounded by b, right? So I will just use like this. I will bound them at the same time by allowing some margins. Okay, so then it is straightforward using this bound. This is not that much hard because each one is bounded. And then we need to show that the only so constant, m is not a constant. It could be constant again if I assumed g greater than 1, but not here. And then we will we need to show this. Expectation of m is obviously positive because g is always positive, and it is not as great as maximum of the expectations, right? Expectation of maximum could be different from maximum of expectations, right? So use that to ah, is it right? I'm not sure. So suddenly I feel like it is wrong. This bound could be wrong, but right, it may be wrong. Oh no. So I'm sorry about this again. This is a big mistake. Anyhow, it may not be bound if g is smaller than g is too small, right? Right. So uh, I had to have a lower bound for g again, simply like g greater than 1. When I made this question, I thought it would be obvious, but I could not think about this case, right? But I'm sorry about that. Anyhow, now, so if you assume g greater than 1, the bound is 1, so it would be simple. Okay. Now let's go to the asymptotic normality. Then all the conditions are the same, but we need to check two conditions about the derivative. So we do the differentiation first. Differentiate like this. Okay. So we are differentiating with respect to beta here and with respect to gamma here, right? So it is a what we say power functions derivative has now natural log here. Then you may simplify like this if you want. Okay, then now from now on I will assume g is greater than 1, right? And then this part does not matter because it is always less than 1 for any gamma. Okay, so we have uh, we can bound everything uh, using like say all the known bounds, like bounded by one, like so, bounded and bounded by b, smaller than b and bounded by one, smaller than b, smaller than beta u, smaller than beta u, smaller than b, and log of g is also bounded by log of b, right? So how nice. It is much easier under this assumption, because of this assumption. This was the assumption that I had to have, I should have made. Now the rank condition. Rank condition, straightforward. Just plug in uh, the truth and take expectation. And to do that, we have to find its determinant not equal to 0. So the determinant goes AD minus BC. So we have this form that is not 0. So this is my another mistake. It has no intuitive way to explain. There is no intuitive way to explain this equality. I cannot interpret what it means. Uh, but nobody got to this point, right? You The common mistake is expectation of a matrix and then take determinant, right? But then you have to take expectation first and then multiply like this and like that. But some of you have done expectation, multiply this first and then take expectation. That is like taking determinant first and then take expectation. This is wrong. This is wrong. Okay. Anyhow, so this is the full rank condition, bounded or bound or considered. And then the GMM asymptotic variance takes this form, and we calculated the derivative G, and omega inverse was simple. So plug them into here. You don't need to do the algebra here. It will be really a digester. Uh, but you can think about how to calculate that. So to calculate that, you calculate G, the derivative first. R is observed variable, Z is observed, G is observed. Just replace unknown parameters with the estimated, right? And expectation with the sample average. That's how you calculate that. And omega is similar, right? The second part is easy to calculate. Uh, Omega should start from here, remember. So the matrix part is easy because you observe Z and expectation can be replaced with sample average. And sigma squared is the variance of epsilon. You can calculate that using the definition of epsilon. So epsilon was defined this way. So replace the true beta and gamma with their estimated counterparts, and expectation replaced by sample average. So it is variance, so you squared it. Everything is so obvious. So it was a huge mistake of mine. I made a big mistake. But anyhow, if I added one assumption, the question was not that bad. It was just my mistake not thinking about the case where g is smaller than 1, right? But my intention was I wanted to show you this model. This model uh, is the best example for GMM because there is no good estimation method other than GMM for this case, right? And it's nonlinear, so nonlinear model does not matter in GMM. So that was the problem, and also verifying those sufficient conditions was not a practical question. Like anyhow, the point here is I want you to understand how the GMM can be used to estimate real, empirical, useful, important economic models. Okay, thanks. I'll see you later. Bye.